All right, howdy folks. In this video, we're going to talk about some of the common questions regarding if compounds are aromatic, anti-aromatic, or non-aromatic. Just as a reminder for those of you that want to download the PDFs of these questions in advance so that you can work through them on your own before watching the video tutorial here, all you have to do is follow us on our Patreon page. All of the PDFs, both of the questions and the filled out answer sheets, are available to those of you that are Patreon followers. Okay, so this is a very common question that arises typically in the chapter where you learn about aromaticity and anti-aromaticity and the Huckel number. And the question goes something like this: if you draw a structure of a cyclic compound, are these compounds aromatic, non-aromatic, or anti-aromatic? And so, of course, to solve that, you have to review some of the fundamentals of what is aromatic or not. And I'll let you do that right now. So please go ahead and pause the video here. Take a few minutes to try to make your best guess for these 8 compounds, and then come back after you have your own answer, and why don't you check that against my answer. So please go ahead and click pause right now. Okay, so coming on back, let's just talk about the top 4 here to begin with. And so I'm just going to zoom in on these 4 compounds. And before I give an answer specifically for these 4 compounds, what I'd like to do is remind you about the general rules at play. So for something to be non-aromatic, it really could be any compound. The overwhelming majority of the compounds that we encounter are non-aromatic. So aromaticity and anti-aromaticity are really truly special properties limited to a specific subset of molecules. And so if you had to guess by default, I would encourage you just to go with non-aromatic. So for things to be aromatic, they have to be cyclic. So you have to have a ring involved. So acyclic systems, regardless of how they're arranged, typically are not aromatic. The second thing that one needs to be is conjugated. And here specifically, we mean that all of the double bonds in the system need to be in conjugation with each other. And so simply being conjugated with, 2 alkenes or 1 extra functional group isn't enough. The whole system has to be conjugated. The next thing there is that it has to be planar. And so it's got to be flat so that all those p orbitals that are sticking up out of the system can talk to each other so that you have that continuous ring of electrons. And then for things that are aromatic, it has to have the Huckel number. And so for the anti-aromatic, then it would be a non-Huckel number. Okay, and so again, because non-aromatic should be your default answer, what I encourage you to do is just check if it's cyclic or not, and then keep going. See if everything is conjugated or not. See if it's planar or not. And then at the very end, see if it has the Huckel number or not. And so let's start with the first one here. I'm just going to switch my pen color. And so this is actually called N-methylpyrrole. It's a relatively common heterocycle. And whenever you have a non-carbon atom, what I encourage you to do is to draw in the lone pair, or to think about if there are electrons there or not. So in this case, my whole system is cyclic, so I can check on the first one. It is conjugated because I can push these electrons around the whole system, and so it meets the conjugation requirement. To put it another way, all of the p orbitals are 1, 2, 3, 4, 5, 6, however many around a ring. It'll be planar, so the 5 atoms have to be a planar system, and that's a normal ring size, so there isn't any paralog strain where we have groups bumping into each other over the top. And if I count my electrons here, I've got 2 for this double bond, 2 for this double bond, and then the lone pair on nitrogen. So that gets me to 6, which is a Huckel number. And so I would call this aromatic. If we compare that to the next heterocycle here, boron does not have a lone pair on it. Actually, boron has an open p orbital when it's trivalent. And so generally we try to think about boron as actually being a Lewis acid in a lot of cases. So compounds like BF3 are really great Lewis acids because they have that open p orbital that's looking to accept electrons. And so because of that, this system again here is going to be cyclic, so that'll be okay. It's still conjugated because that open p orbital is much like a carbocation that can be in resonance with an adjacent double bond, and so it is still conjugated. It's going to be forced to be planar. There isn't going to be enough wiggle or wobble for the bonds to get out of each other's way, and so it checks that. And in this case, it only has 4 electrons, so it has 2 here and 2 from that double bond, and the open p orbital doesn't bring in or count for any electrons. And so this would be a 4-electron system, and I would imagine this to be a non-Huckel number then, and so I would label this as being anti-aromatic. Okay, the next compound here is one where, again, we're going to invoke some resonance structures, and so I'm actually going to redraw this compound. Like so. And if I make a negative charge, then I have to have a positive charge. And so we're going to polarize it based on that carbonyl, that CO, is the oxygen is more electronegative, and so it's going to pull the electron density towards it, and we'll leave a carbocation at that center. And so this would be a resonance structure. So I'll go ahead and add my resonance arrow there. All right, so it's still going to be cyclic. It is now conjugated, so I have a p orbital at every one of these positions going around, and they're all in the same ring system, so it should still be conjugated. It may or may not be planar, but 7 is getting close to when we can start having puckering and ring torsions to try to really knock things out of conjugation. And so let's hold off on planar and go to the Huckel number here. So in the ring now, I have 0 electrons for that positive charge, and I have 2, 2, and 2. And so if I have 3 double bonds, all of which are 2 plus 0, that should get me to 6. And so that would be a Huckel number. And remember, if systems can planarize to become aromatic, they'll prefer to do so because aromatic is stabilizing overall. And so I would label this one as being aromatic. Okay, the next one here is kind of an unusual looking molecule. And this is one where we're going to have to really check our conjugation. So it's going to be cyclic just like all the other ones. And it'll be planar for the most part. Where this one is going to run into some problems, I think, is conjugated. And if we think about it, there is a p orbital at every one of these positions. And it actually does have 10 electrons in it. So if I go through, I've got 2, 2, 2, 2, 2. So there's 5 double bonds. And so overall, that's a 10E system. But this molecule is not going to be aromatic. And the reason it's not going to be aromatic is because there's no way for this p orbital to talk to this p orbital. And so to illustrate that, let's just arbitrarily ionize one of these double bonds. And so I'm going to go back to the black marker here. And it doesn't really matter if we pretend we have plus and minus, but what I've done here is arbitrarily just polarized one of those double bonds into its charges. And now the goal is to see if we can get all of the orbitals to talk to each other. And so I can move these electrons over now and make a resonance structure. Like so, and that's a little ugly, so let me try to just redrawing that a little bit. But now there's no way for this positive charge to get delocalized out here. And the reason for that is now we have a tetrasubstitute carbon at the center. And so while you can move a charge from any of the 2 adjacent kind of prongs sticking out, there's no way for you to get from the 1 to the 3 position. And so this molecule is actually going to fail the conjugation test. And so because of that, I'm going to label this one as non-aromatic. And it's because, again, we can't move this positive charge out to this point, at least not without making something that's super, ridiculous. I guess if you wanted to, you could put all 5 cations around the outside and then have all 5 negative charges in the middle, and then you'd have 10 electrons in the middle. But there's no way you're going to pump that much electron density due to electron-electron repulsion. So this one is non-aromatic. All right, I'm going to switch here to the green pen so that we don't confuse it with the ones up above. So this cyclopropenone, we can have a resonance structure again where we polarize that carbonyl oxygen just like we did before. And now we have a system that is going to be cyclic, so that'll check. It's going to be conjugated, so that'll check. It's going to be planar, because 3 membered rings by definition are a plane. And then 2 is actually the lowest Huckel number. And so this one is actually going to be aromatic, which is kind of an unusual one. Let's skip the middle one here for a minute and go on to the easy one. So this is Cyclooctadiene, which of course is one of these very famous molecules that, I'm sorry, Cyclooctatetraene, which is one of these famous molecules that should be anti-aromatic, but it ends up being non-aromatic because as I have it drawn here, it is not planar. And so this is going to be non-aromatic because it's not planar. And I've tried to draw it that way on purpose. Okay, so the next one here then is going backwards, this kind of bicyclic system. And this one's kind of an unusual one because we have, you know, a lot of double bonds. And overall, the system, if we just check here, it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's good. And I think that there's so it's definitely cyclic. It's definitely conjugated, so all the double bonds in a row are very similar. So that's good. It kind of goes double, single, double, single, double, single, all the way around. Because it has this bridging carbon-carbon bond here, that's going to force it to be planar, so it'll check that. And 10 is going to be a Huckel number, and so this one should be aromatic. The one thing I'll point out here is it is kind of fun to draw this resonance structure where we actually planarize this one position. And so if we do that, we should end up with a negative charge. And then a positive charge. And if I move these electrons down, then I can move these on up, and we'll have a new resonance structure here. I want a bridgehead, I'm going to put the minus down here. And then I've got 2, 3, 4, 5, 6, 7. So hopefully that's the right number of bonds. All right, and so now in this resonance structure, what I can see is I clearly have one 7-membered ring that has 3 double bonds in it and a positive charge. And so that actually very closely resembles this one from up here, where we had 3 double bonds and a positive charge. And then this one is a 5-membered ring with 2 double bonds and 1 negative charge. And so that should resemble the famous cyclopentadienyl anion, which is a very classic aromatic species. And so even if you can't quite see it from the neutral compound, sometimes it's fun to draw out these resonance structures where you can see how both halves can actually be aromatic all on their own. All right, the last one here is a heterocyclic compound, again with oxygen. And when you have hetero atoms in the system, I always encourage you to draw your lone pairs in. And as it looks right now, it's not quite clear that it's fully conjugated, but I can push these electrons around again. And so if we do that, we can have a resonance structure. That now looks a lot more like benzene. And so now we clearly have a 6-atom system that is cyclic, and it's got 1, 2, 3 double bonds in it. And so often when you have these hetero atoms involved, what I encourage you to do is to draw out where the lone pairs are and see if there's any resonance structures that might make sense to help polarize the system and arrive at an aromatic compound. All right, and so here's 8 examples of things that we've labeled. And hopefully you can go through these rules all on your own now and see which ones are aromatic or non-aromatic. Again, the really nice thing about this is if you use these 4 criteria, it'll be very difficult for you to be wrong, because most of the tricky ones have to do with things like being planar or being conjugated. And so you can use those as your test first. All right, hopefully you enjoyed this video. If you did so, please go ahead and subscribe to the YouTube channel. Again, the number of subscribers lets us know that these are helpful videos to people, and it'll provide encouragement for us to try some more. If you want access to the PDF notes, again, you can go ahead and become a patron follower. And if you do so, you can get and download the PDFs, both of the questions ahead of time, but then also the answers after I've solved them. And so please go ahead and do that. All right, thank you, and please enjoy the next